The group of units, GM. So this is the group of units in the ring Z mod M. Okay, start with the following definition. So if A and M are integers, an integer B is called a multiplicative inverse of A mod M, denoted A to the negative 1 power, if A times B is congruent to 1 mod M. And then if I'm working in the ring Z mod M, we'll use, let's start with A bar being an element of ZM, and we'll call it a unit if it has a multiplicative inverse. So that's just a general concept. A unit in a ring is an element that has a multiplicative inverse. So in this case, there would have to be an element B bar in the ring Z mod M such that A bar times B bar equals 1. And these two concepts of multiplicative inverse are equivalent. So an integer A has a multiplicative inverse mod M if and only if A bar is a unit in the ring Z mod M. Now it's easy to verify that multiplicative inverses, if they exist, are unique. And it's also easy to check that not all elements in ZM have multiplicative inverses. For instance, in Z4, 2 has no multiplicative inverse. Right? No matter what you multiply 2 bar by, you would never end up with 1. And so when does an element have a multiplicative inverse? There's a simple lemma here. An element A has a multiplicative inverse, mod M, if and only if A is relatively prime to M. Or equivalently, A bar is a unit in ZM if and only if the representative A is relatively prime to M. All right, let's take a look at the proof. These are the same statement, just written in the different language. So, okay, why does A have a multiplicative inverse? If and only if A is relatively prime to M. So being an if and only if statement, let's do two directions. So first, suppose A has a multiplicative inverse. That is, there exists a B in the integers with AB congruent to 1 mod M. Well, that would imply that AB equals 1 plus some multiple of M for some integer k. And thus, we have a linear combination adding up to 1, that A times B minus K times M equals 1, and that implies that A and M are relatively prime. By what we saw in an earlier chapter. Remember, if there was any divisor of A and M, then it would have to divide this linear combination, which would mean it's a divisor of 1. Okay, so that's one direction. Conversely, suppose that AM equals 1. Well, then by GCD-LC theorem, there exist X and Y in Z such that AX plus MY equals 1. So 1 is a linear combination of A and M. But that equation tells me that A times X is 1 minus M times Y, which means that AX is congruent to 1 mod M. And therefore, X is in fact a multiplicative inverse of A. Straightforward. The cancellation law for modular arithmetic. So let ax and y be integers with ax congruent to ay mod m. I'd like to just cancel the x out, or cancel the a out on both sides of the equation, but you can't do this always. What we need is that a and m are relatively prime. So if a is relatively prime to m, then I can cancel the a on both sides, and we simply get x is congruent to y mod m. More generally, if they are not relatively prime, I'll let d be the GCD, and then I can say x is congruent to y mod m divided by d. So it's not congruent mod m, but rather the smaller modulus m over d, which is a weaker congruent statement. Okay, start with part 1. So suppose ax is congruent to ay mod m. I think you've caught on to my little symbol here. That's an S and a P put together for suppose. The x is congruent to ay mod m. Then what can we say? Well, if a and m are relatively prime, that's another assumption, then a has a multiplicative inverse. Mod m. And so I just take that equation and multiply both sides by a inverse. So a inverse ax is congruent to a inverse ay. And then after using the associative law and the definition of multiplicative inverse, we get x is congruent to y mod m. Okay, part 2. Okay, so let d be the GCD. Now what we have to do, because I'm changing modulus, is just go back to a linear equation in the integers. So ax congruent to ay mod m means that ax equals ay plus km for some k and z. And now I can observe that every one of these terms here, we got 3 terms, has a factor of d. So I'll just divide everything through by d. And think of this as an equation a over d. X is a over d y plus k times m over d. So remember, d is a divisor of a and m, so although I've written them as fractions, these are really integers. And what is this equation telling me here? This says that a over dx is congruent to a over dy mod m over d. All right? Because these two things differ by a multiple of m over d. Aha! Now we can go back to case 1 and say, since a over d and m over d are relatively prime, right? We've divided out the greatest common factor. That was a homework problem. We can apply part 1 and just cancel the a over d on both sides. QED. That's exactly what we wanted to prove. Okay, the group of units mod m. So for any positive integer m, I'll let gm denote the set of all units in Z mod m. So as we had observed earlier, if you look at the set of units in any ring, this forms a group. And gm thus is an abelian group under multiplication. So let's again just review that concept again. So to show something's a group, it has to be closed under multiplication. So if A bar and B bar are elements of the group of units, then A bar, B bar, the product, is a unit. In fact, we showed in that earlier discussion that the inverse of A bar, B bar is just the inverse of B times the inverse of A. Of course, the order doesn't matter here. It's a commutative ring. So it's closed under multiplication. Property 1, the identity is in here, 1 bar. And the third property is that if A is a unit, then it has an inverse, and the inverse is a unit. Okay, so we have this group, and one of the things we want to study this semester is what type of abelian group is this? So if you've studied group theory, you know that abelian groups have very nice structures. So is it a cyclic group, or is it a Cartesian product of certain types of cyclic groups? That's one of the goals we want to do next. Okay, now let's introduce the Euler phi-function. So for any positive integer m, the Euler phi-function is just the number of positive integers less than or equal to m that are relatively prime to m. It's also called the Euler's totient function. So if I want to look at phi of 9, for instance, I just write down all of the numbers from 1 to 9 that are relatively prime. We've got to skip 3. So 4, 5, 6, skip 6, 7, and 8. So there are 6 numbers relatively prime. So phi of 9 is 6. And by the observation we just proved that an integer has a multiplicative inverse mod m if and only if a is relatively prime to m, we immediately see that the order of the group of units is phi of m. So it follows immediately from the fact that A bar is in Gm if and only if the GCD of A and M is equal to 1. Okay, now let's see, are we ready to do a formula? No, we'll do this one first. If P is a prime, then every non-zero element of Z mod P is a unit. Thus, ZP is a finite field with P elements. So recall, a field is a commutative ring with unity in which every non-zero element has a multiplicative inverse. So why in Z mod P is this true? Is every non-zero element a unit? Well, if P is a prime, then for 1 less than A less than or equal to P minus 1, we certainly have GCD of A and P equals 1. A and P have no common factor, and so A has a multiplicative inverse, mod P. And so every non-zero residue class has a multiplicative inverse. And ZP has P elements in it altogether. 0, remember, is extra. So all non-zero elements have to have a multiplicative inverse. And that's all that's going on there. Another terminology, we'll say that a set of integers, a1 through am, is a complete residue system mod m if the values are distinct mod m. That is, z mod m has these m values as representatives. And we'll call a set of phi of m integers a reduced residue system if they represent the group of units mod m. So, for example, if I'm in Z9 and I want to look at GM, so G9 would be 1 bar. This is the canonical set of representatives here, 7, 8. But there's no need to use those particular numbers. I could just as well have added any multiple of 9. I could have used 10 here. I could have subtracted 9 and used negative 7. I could have added 18. I could have left 5 alone, etc. You get the idea. And so the set of integers, 10, negative 7, 22, 5, negative 2, and 8. So this is a subset of just the ordinary integers. And that would be called a reduced residue system mod 9.